All right, in this video, I'm going to talk about bond polarity, and then I'm going to talk about molecule polarity and how that's related to bond polarity, because sometimes people tend to get them a little bit confused. All right, so we're going to start by talking about bond polarity. Now, in Unit 3, we talked about bonds as being either ionic or covalent. And we know that ionic compounds are composed of a metal and a nonmetal. And we know that covalent compounds have two nonmetals. So nonmetal and nonmetal, two or more. Okay, now, there's actually quite a lot of variation within covalent compounds. And there are two types of covalent bonds. You can have polar bonds and you can have nonpolar bonds. Now, polar bonds exist when I have an electronegativity difference of greater than 0. Now, you might be like, well, how on earth am I supposed to know that? We'll give you charts a lot of times that have electronegativity values, okay? Now, if you're given a chart, you should check and make sure two atoms have different electronegativity values. So for example, let's say I had a bond between carbon and nitrogen. Carbon has a value of 2.6 and nitrogen's value is 3.0. So they would have a polar bond because they have an electronegativity difference that's greater than 0, right? They're different elements with different electronegativities. Most of the time, you can recognize polar bonds because they occur between different atoms, okay? So if I have two different atoms, I can assume the bond is polar. Now, if you're given those values, check and make sure they have different electronegativities. But if you're not given the values, you can assume different atoms means different electronegativities. Now, nonpolar bonds occur when I have an electronegativity difference that's 0. Okay, and so this is between two atoms of the same element. Now you might be wondering why electronegativity difference is even significant. So let me show you. All right, so let's say that I had a bond between hydrogen and chlorine. And then I had a bond between hydrogen and hydrogen. Now we know that chlorine is more electronegative than hydrogen based on the trends, and we could also confirm that with this table. Chlorine has an electronegativity of 3.2, hydrogen is only 2.2. So what that means is that they're going to share the electrons, but they're not going to share them evenly. Chlorine has a greater attraction for the electrons, so we would draw an arrow to represent the dipole moment. Okay. This shows which way the electrons are being pulled. They're going to be pulled towards the atom with greater electronegativity. Since the electrons are being pulled more towards chlorine, we would say chlorine has a partial negative charge and hydrogen has a partial positive charge. Okay? So this is a polar bond. Now, in this bond, these are two identical atoms. So you can't say that one has a greater pull on the electrons. They're pulling the electrons exactly evenly. So this is a nonpolar bond. And in this nonpolar bond, electrons are shared evenly. So there's no dipole moment. They're just being shared evenly between those two identical atoms. Now, in order to figure out if a molecule is polar or nonpolar, we're going to have to look at the overall shape. Now, if the bonds are nonpolar, the molecule has to be nonpolar. But sometimes we can have polar bonds but have an overall nonpolar molecule. So I'm going to draw two examples. I'm going to draw carbon dioxide and I'm going to draw water. Now we know from Unit 3 that when we draw the Lewis structure, we can figure out the shape. So this is linear and this is bent. And the difference that makes this bent is that this has lone pairs on the central atom. Okay? Now both of these have polar bonds, right? And they have polar bonds because oxygen is more electronegative than carbon, right? So the electron is going to be pulled more in that direction. Same with the other bond. Here, oxygen's more electronegative than hydrogen, so we would draw them pointing inward. But these are exactly opposite. So the dipole moments cancel out, okay? This is a completely symmetrical molecule. And so that means that the dipole moments cancel out. The addition of the lone pairs makes this asymmetrical, so the dipole moments do not cancel out. They sort of cancel each other out side to side, as you can see, but there's still this net upward pull. So the dipole moments do not cancel out. Okay? And so this is overall nonpolar. So this is a nonpolar molecule. And this is a polar molecule. Now they both have polar bonds, but here, since the dipole moments cancel out, it's a nonpolar molecule. They don't here, so it's a polar molecule. The easiest way to tell is to look for a lone pair on the central atom. If there's no lone pair on the central atom, it's typically nonpolar. If there is a lone pair, then it's typically polar. Okay? Now, of course, there's all kinds of exceptions when we start talking about larger molecules. If these two atoms were different, then the dipole moments wouldn't cancel out. But this is a good place to start, looking for a lone pair on the central atom. Okay? All right, so then take a look back at your notes and your homework and see if you have any questions for me.